This is example 3 in section 3.2. And here we're told that y equals f of x equals 1 over x squared. So this is our function that we're working with, just written as either y or f of x. And the reason why we've got both of those function notations is because this problem is going to force us to think about the other notations for the derivative. So notice it tells us to find dy dx and then find f prime of -3. So recall from the last video that dy dx and f prime both refer to the derivative of a function. This is from either Newton's notation or Leibniz's notation. So that is what we're going to be doing here. We're going to find the derivative. So let's start with writing our definition of the derivative, which is still the same. Even though we're using Leibniz notation here, it's still the exact same definition. The limit as h approaches 0, f of x plus h minus f of x all over h. Okay. And we're going to go through the exact same process here as we have been. So start by plugging in your x plus h into the function. So we'll have limits, h approaches 0, 1 over x plus h squared. That's f of x plus h, and then minus f of x, which is 1 over x squared, all over h. Okay. Now, to start evaluating this limit, this is one of those interesting ones where we've got a complex fraction situation going on here. We got some fractions up in the numerator, and then the thing overall is a big quotient. So let's do a little switch here in the way we're writing this. If you'll recall from a couple videos ago, I think in 3.1, here where we're dividing by h, I instead often like to write that as multiplying by 1 over h instead, just to help keep things a little more orderly. But if you like keeping it all as a big fraction over h, that totally works. That's great. I'm going to put 1 over h here as a multiplier, but if you do it the other way, we should end up in the same place. Okay, so I just rewrote the limit expression there. All right, now we'd like to get a common denominator for these two terms. Okay, and that common denominator is going to be x plus h squared times x squared. So we'll need x squared on this first fraction. And then we'll need x plus h squared on this second fraction to get that common denominator, like so. Okay, now let's combine those fractions. 1 over h there, and then we'll have x squared minus x plus h squared all over our common denominator, x squared, x plus h squared. Okay. And we're just doing some algebra here. We're going to try and simplify things down. So we've got x squared and then minus, okay, x plus h squared would be x squared plus 2xh plus h squared. There we go. Keep that denominator. All right. During any of these example problems, if you want to pause the video and try it out yourself before I get to answer, that is totally cool, by the way. So if you know where we're heading with this, pause and finish it up here. Then you can check your work. All right. So here, let's distribute that negative. We'll have x squared minus x squared. Something nice is going to happen there. Minus 2xh minus h squared all over x squared, x plus h squared. Okay, so the nice thing that's going to happen, x squareds are gone. Cool. Okay, so we have the limit as h approaches 0, 1 over h times, let's see, in the numerator here, I am going to go ahead and factor out this h right here, just to help speed our process along a little bit. So I'm going to factor out h, and then we'd have negative 2x minus h. Okay. So, all right, see if I were to distribute, it's the exact same thing. So there we go. Okay, so we factored out the h, and the reason why I did that is because you know what's going to happen. The h's are going to cancel. So that's the good thing that we keep looking for in these problems. So now we've got the limit as h approaches 0 of negative 2x minus h over x squared times x plus h squared. And since that h right here canceled out, we're able to use direct substitution now. So this is good. Negative 2x minus 0 over x squared times x plus 0 squared. Okay, so we've got negative 2x over x squared times x squared. Cool. Now a little something interesting will happen there. We can cancel this x in the numerator with one of the x's in the denominator. So notice that just one of those went away. So this is down to first power there. And so our answer is going to be negative 2 over x times x squared, which would give us x cubed down in the denominator. Okay, so that is the derivative of our function. The derivative of 1 over x squared is negative 2 over x cubed. All right. So that is dy dx in the Leibniz notation. Note that dy dx means the exact same thing as f prime of x. Dy dx means the same thing as f prime of x. So that's going to help us do this second part of the problem really quickly, because when we're told to find f prime of negative 3, literally all that's saying is that negative 3 is going to be your x value for this next part. But we don't need to go back and compute anything new. We don't need to go find f prime or anything because we've already found it in finding dy dx. That is f prime right there. So dy dx equals f prime of x equals negative 2 over x cubed. Same thing there. All right, so to find f prime of negative 3, we just need to plug in x equals negative 3. So negative 2 over negative 3 cubed. All right. And that would look like negative 2 over negative 27, or positive 2/27 for the result there. Okay, so there's our derivative, and there it is evaluated at a particular value. Now, one last thing on this problem here, since it is a lot of notation, the notation for this type of thing, plugging in a value into the derivative function, we have just seen it in that Newton notation so far. In Leibniz notation, this looks a little bit weird. So here's Leibniz notation. Okay, so for Leibniz notation on this, we would say dy dx, so there's the Leibniz, and then a big vertical line, and then you put x equals -3 down here. All right. So that big vertical line just means evaluated at. It's an evaluation bar. So you would read this as dy dx evaluated at x equals -3. So math can be like a whole nother language sometimes. Different symbols represent different words, so you have to be able to translate. Yeah, like the derivative of f at -3. And this means the derivative of y equals f of x at -3. So same thing, same thing. So it's going to be that same result, -2/27. All right, so there we go with all our notations.